Look, if you've spent any time in the AI space recently, you already know it is incredibly easy to build a flashy demo in a Jupyter notebook. But taking that exact same demo and making it survive contact with thousands of concurrent users, yeah, that is an entirely different beast. Welcome to this explainer. Today, we are shifting completely away from the hype of training models, and we're looking at the brutal reality of designing, deploying, and scaling resilient AI inference systems. We're putting on our cloud architect hats and going straight into the trenches to look at AI strictly through the lens of distributed systems, open standards, and production-grade infrastructure.
Here is the hard truth. Most AI projects don't fail because of bad models. They fail because of bad systems. That illusion of a successful, perfectly contained notebook completely shatters the second you hit the production wall. Building AI isn't just about data science anymore. It is fundamentally a distributed systems problem. Think about it. A model is really just a massive, compressed file of weights. It literally does nothing until it's served, fed real-time data, and wrapped in an architecture that can handle the sheer, unpredictable chaos of generative outputs. If your underlying system is brittle, I don't care if you have a brand new billion-parameter foundation model, it's going to crash just as fast as a 10-line Python script.
So here is our roadmap for today. We'll start with AI systems in reality, then break down the core production architecture. After that, we'll dive into inference and scaling, dissect some critical production failures, and finally, look at the future of AI infrastructure.
Okay, Section 1. Let's establish what AI engineering actually looks like when you rip it out of a local environment and deploy it into a real cloud cluster.
This completely illustrates the paradigm shift we're talking about. On one side, you have your notebook. It's a pristine little world. Single user, static data, unconstrained compute, and absolutely zero service-level agreements. But production reality? It's a war zone. If you treat an AI model like a standard deterministic REST CRUD app, you are basically begging for a catastrophic collapse under load. Why? Because traditional systems are highly predictable. A standard database query takes roughly the same amount of time every single time. But foundation models, they are stochastic. Generating a quick hello takes milliseconds, but generating a 500-word essay ties up your GPU for seconds. Because of this massive non-determinism, if you just expose a model directly to user traffic, your strict latency SLAs will be completely destroyed. The very first time you get a spike in long-form generation requests, your system backs up. Network latency spikes, requests time out, and your entire service just falls over.
Let's move to Section 2, Core Production Architecture. How do we actually build this out so it doesn't collapse? You have to design for failure, and more importantly, you have to design for back pressure. Picture this pipeline in your head. Requests first hit an API gateway. This is your primary shield against massive traffic spikes. From there, they absolutely do not go straight to the model. Instead, they flow into a managed message queue, something like Kafka or PubSub, to level the load. This is how we handle back pressure. Those requests then get dynamically batched and routed to our inference pods. These need to be stateless, containerized serving instances running in a Kubernetes cluster totally decoupled from your state. When they need context, they quickly query a generic vector store or Redis cache. And critically, sitting underneath every single piece of this is a robust observability stack doing end-to-end distributed tracing on every hop of that journey.
Now, even in its simplest foundational form, whether you're hitting a managed service or running an open-source local inference server, the base model API requires rigid guardrails. You can't just trust the output. You must immediately bolt on an orchestration layer to ensure data flows reliably and safely. Say a user asks a toxic question or the model hallucinates a dangerous command, your system needs output guardrails, usually running on much smaller, cheaper CPU instances, to intercept, evaluate, and sanitize that payload before it ever makes it back to the user.
All right, Section 3, Inference and Scaling. We have the blueprint, now let's talk about the hardware bottlenecks that will actually keep you up at night.
Every single architectural choice you make here is a brutal trade-off. Large language model inference has two distinct phases. First, you have the prefill phase. This is when the model reads your prompt. It processes all those input tokens in parallel, which means it is incredibly compute-bound. Second is the decode phase. The model generates the answer one token at a time. This is memory bandwidth bound because it's autoregressive. Listen, if you don't aggressively decouple your compute-heavy prefill instances from your memory-heavy decode instances, they will violently compete for the same GPU resources. Imagine a GPU busy decoding a long response, and suddenly a massive new prompt arrives. The prefill job demands massive compute, instantly starving the decoding job, and your user's text generation just grinds to a complete halt. You have to disaggregate them. To manage all this chaos, you must rigorously separate your metrics. Time to first token, or TFTFT, is your user experience metric. It is literally how long a user stares at a blank screen waiting for something to happen. You want to minimize this at all costs. Then there's time per output token and overall throughput, measured in tokens per second. Here's the uncomfortable reality of AI engineering. Optimizing time to first token for a snappy user experience almost always directly conflicts with maximizing tokens per second to control your cloud compute costs. These metrics are at war with each other. As any staff engineer dealing with massive scale will tell you, you can easily double your system throughput, but only if you're willing to let user latency degrade. It is a strict, unavoidable engineering trade-off.
So how do we scale efficiently without completely destroying that latency? We use continuous batching. Think of traditional static batching like a bus waiting at a terminal. It has to fill every single seat before it leaves, so everyone waits for that last person. It's terrible for latency. But continuous batching, or in-flight batching, is like a bus picking up and dropping off passengers dynamically while moving at a steady speed. As soon as one request finishes its generation, the system instantly swaps in a new request from the queue to utilize that empty slot on the GPU. It keeps hardware utilization extremely high without forcing early requests to wait around for later ones.
We achieve this massive scale by leaning heavily, and I mean heavily, into Kubernetes-native patterns. We absolutely do not scale based on standard CPU metrics. Instead, we use horizontal pod autoscaling driven by queue depth. If our message queue backs up, Kubernetes automatically spins up more inference pods. We apply strict GPU scheduling constraints, maybe even routing specific matrix math to TPUs where it makes sense, and we aggressively mitigate cold starts by implementing multi-tier caching. Think about it. If you can intercept a duplicate semantic request at a simple Redis cache layer before it ever wakes up your expensive GPU pods, you've just saved a massive amount of your compute budget.
Moving into Section 4, even with perfect scaling, things break. Let's analyze 5 critical production failures purely from an infrastructure perspective. These are the exact failure modes that will wake you up at 2 a.m. Number 1, API timeouts. Scenario: user traffic spikes during a launch and your app starts dropping requests left and right. The root cause? You treated stochastic AI like a synchronous REST call. The architectural fix is async, queue-based load leveling. Never expose the model directly to the user. Number 2, silent degradation. Over a month, your model's accuracy completely tanks because the way users phrase prompts have subtly shifted. The fix? Implement robust metadata tracking and continuous data drift alerts. Number 3, system paralysis. An engineering team spends 6 months building complex semantic routing and agentic flows before they even have 100 daily active users. It's massive technical debt. Just start with a simple exact match cache. Number 4, blown budgets. You process tens of thousands of offline document summaries on expensive, real-time online instances and drain your entire cloud credit allocation in a single weekend. Actually, scratch that, I've seen it happen in hours. The fix is routing non-urgent jobs to cheaper, asynchronous batch APIs, utilizing tools like Queue and Kubernetes to manage those workloads. And 5, undebuggable errors. A user request fails and you have absolutely no idea if it was the initial prompt, the vector database retrieval, or the final model generation. You are flying completely blind. You must have end-to-end distributed tracing in your orchestrator so you can pinpoint the exact microservice that failed.
Finally, Section 5, the future of AI. Let's look at the forward evolution of these systems as we wrap up this architecture breakdown. The landscape is shifting incredibly fast. Future engineering teams won't be hand-wiring bespoke Python scripts just to call a model. Instead, they will be maintaining internal AI platforms that act as strict, cost-aware Kubernetes-native orchestrators for highly complex agentic workloads. We are moving toward a world where systems autonomously spin up temporary pods, execute a multi-step reasoning task, query a production database, and, most importantly, tear themselves down, all while continually optimizing for the absolute cheapest available compute hardware in the cluster.
So what's the ultimate takeaway here? Your success as a cloud architect hinges entirely on your ability to step away from the notebook and build resilient, scalable infrastructure. Literally anyone can make a large language model generate text once. But can you engineer a system that does it 10,000 times a second? Can you mitigate cold starts, handle severe network back pressure, and do it all without bankrupting your company in the process? That is the real engineering challenge. Are you just calling an API, or are you actually engineering reality? Think deeply about that as you design your next cluster. Thanks for joining me on this explainer. I'll see you in the next one.